The theory of relativity was introduced by Albert Einstein at the beginning of the 20th century. What is its essence? Let's consider the main points and describe the toe in clear language. The theory of relativity practically eliminated the inconsistencies and contradictions of physics of the 20th century, forced a radical change in the idea of the structure of spacetime, and was experimentally confirmed in numerous experiments and studies. Thus, toe formed the basis of all modern fundamental physical theories. In fact, this is the mother of modern physics. To begin with, it is worth noting that there are two theories. Of relativistical relativity theory SRT considers physical processes in uniformly moving objects. The general theory of relativity T describes accelerating objects and explains the origin of such phenomena as gravity and the existence of particles of gravitons. The theory is based on the principle of relativity, according to which any laws of nature are the same for bodies that are stationary and moving at a constant speed. And from such a seemingly simple thought it follows that the speed of light 300 meters per second in a vacuum is the same for all bodies. For example, imagine that you were given a spaceship from the distant future, which can fly at great speed. A laser cannon capable of firing photons forward is mounted on the bow of the ship. Relative to the ship, such particles fly at the speed of light, but relative to a stationary observer, they would seem to fly faster, since both speeds are summed up. However, this is not actually happening. An outside observer sees photons flying 300 meters per second. As if the speed of the spacecraft was not added to theme, it is clear that the SRT appeared earlier and, in fact, is part of the GRT. Let's talk about it first of all. All bodies are falling at a constant speed, not accelerating. Let's do a scary thought experiment. Imagine that you are riding in a closed elevator cabin and are in a state of weightlessness. Such a situation could arise only for two reasons: either you are in space, or you are falling freely together with the cabin under the influence of Earth's gravity. Without looking out of the booth, it is absolutely impossible to distinguish between these two cases. It's just that in one case you fly evenly, and in the other with acceleration. You'll have to guess. Einstein's theory of relativity briefly and clearly. Relativity theory. Science, interesting. Physics, long post. Albert Einstein. Perhaps Albert Einstein himself was thinking about an imaginary elevator, and he had one amazing thought: if these two cases cannot be distinguished, then falling due to gravity is also a uniform motion. The motion is simply uniform in four-dimensional spacetime, but in the presence of massive bodies, for example, planets of the solar system, it bends in uniform motion, is projected into the usual three-dimensional space in the form of accelerated motion. Einstein's theory of relativity briefly and clearly. Relativity theory. Science, interesting. Physics, long post. Albert Einstein. Let's look at another simpler, though not entirely correct example of the curvature of two-dimensional space. You can imagine that any massive body under itself creates some kind of shaped funnel. Then other bodies flying by will not be able to continue their movement in a straight line and will change their trajectory according to the bends of the curved space. By the way, if the body does not have so much energy, then its movement may be closed at all. It is worth noting that from the point of view of moving bodies, they continue to move in a straight line because they do not feel anything that makes them turn. They just got into a curved space and, without realizing it, have an indirect trajectory. Einstein's theory of relativity briefly and clearly. Relativity theory. Science, interesting. Physics, long post. Albert Einstein. It should be noted that four dimensions are curved, including time, so this analogy should be treated carefully. Thus, in the general theory of relativity, gravity is not a force at all, but only a consequence of the curvature of spacetime. At the moment, this theory is a working version of the origin of gravity and is perfectly consistent with experiments. Light rays can bend when flying near massive bodies. Indeed, distant objects have been found in space that hide behind others, but light rays bend around them so that light reaches us. According to GRT, the stronger the gravity, the slower time passes. This fact is necessarily taken into account when GPS and GLONASS work, because their satellites have the most accurate atomic clocks that tick a little faster than on Earth. If this fact is not taken into account, then in a day the coordinate error will be 10 kilometers. It is thanks to Albert Einstein that you can understand where a library or a store is located in the vicinity. And finally, GRT predicts the existence of black holes around which gravity is so strong that time simply stops nearby. Therefore, light trapped in a black hole cannot leave it be reflected. In the center of a black hole, due to the colossal gravitational compression, an object with an infinitely high density is formed, and this, it seems, cannot be. Thus, GRT can lead to very contradictory conclusions, unlike the special theory of relativity. So the bulk of physicists did not fully accept it and continued to look for an alternative. But she also manages to predict many things successfully. For example, the recent sensational discovery of gravitational waves confirmed the theory of relativity and made her remember the great scientist with his tongue hanging out again. Love science, read Wikineans.